people. Hope everyone's doing okay today. Does anyone have anything on their mind they want to talk about before we get started? Okay, not seeing anything. Want to check, make sure everybody can hear me. So, here we go. Can anyone not hear me? Okay, appears like we're all right with that. I'm going to share my screen. We'll take a look at Blackboard and Sapling, make sure everybody's in the same place. And while we're going there, I want to apologize to some of you guys. You sent me an email, I think, yesterday, and I didn't really see it until later in the day, so I didn't have an opportunity to respond to it regarding some of the homework. So I moved the date out a couple days for the homework that was going to be due last to make sure everyone knows how to do all the problems. So if you sent me an email and all I said was, well, you know, we're gonna extend the due date, and I'll get back with you. Yeah, I'm going to get back with you on your question. So, nope, should be no worries there on that. These announcements are not really that current. Let's see, what is it? Oh, wait a minute, there is one on Thursday. Sorry. Oh yeah, that's what I was writing about. So if you're having trouble with a sapling assignment, I can look at your previous attempts and give a suggestion. Just email me the chapter number and the name of whatever you're working on and whether it's homework or topic introduction. And then tell me the question number, and then I can find it. I don't need a screenshot. That really doesn't give me anything to go on, really. Because I don't remember what all these questions look like. I have some of them I've not looked at in a couple semesters now. So, but if you'll give me the chapter and name and homework or topic and question number, I can see exactly what you're seeing. So anyway, that's the deal with sapling. So I know the task list is not up to date because I changed the due dates on some of the sapling stuff. And so I don't think there's anything else there to talk about. Let's take a look at sapling. Yeah, the thermodynamics chapter was going to be due last night. I pushed that out to the 26th. We should be okay with doing that. We really don't have that much remaining to do, so should not be a problem. And what else? I still have not really come to a conclusion on whether we should have an exam 4 or not. I realize how it would be probably, you know, the best as far as keeping the weights of the grading the same. So anyway, I'll try to give that some more thought this weekend and expect an announcement over the weekend on whether we're going to have an exam 4. If we do have an exam 4, the earliest it could be would be a week from Monday. So there would not be an exam this next week. There could be one the following week at the earliest, and I don't know for sure on that. Okay, guys, so I'll stop sharing this and see if we got any questions now. So do we have any questions? Got some people that came in a little bit later, so I need to get you put in a group. Not getting any questions. Okay, well, I have a question. I was thinking about this right before we started up, and that is anyone planning on taking any chemistry classes over the summer? Which the only thing I think of is you were going to take Chem 132. So if you were planning on taking Chem 132, please raise your hand just so I have sort of an idea what's going on there. Okay, Edgar's planning on taking Chem 132. Anybody else? Okay, Martiza, gotcha. No one else planning on taking Chem 132 over the summer. I know for, probably most of you, if you are going to be to take any more chemistry, you're planning on taking first semester organic. And so I don't believe we're doing that this summer. I don't remember seeing that. So anyway, that would not be until the fall. So well, I should ask that. Is anyone planning on taking Chem 234 this fall? Raise your hand. Okay, I got Noah. Anyone else? Chem 234. Organic. First semester organic. Okay, Janet, gotcha. Brianna, got you. Anyone else? Oh, there's a bunch of you. Yulia? Anyone else? I have no idea what the situation is going to be for fall. They're not going to tell us until the last moment probably. But as for summer classes, they are going to be online. That's already been announced, so they will not change on that one. Okay. If you have any questions about any of that, kind of shoot me an email. I'll try to get you some information if I can. Okay, so I think that's everything. We'll go ahead, get going on the lecture. We're, of course, still in the electrochemistry chapter. So we're in chapter 17, electrochemistry, and looking back at my notes here, we had just done standard reduction potential is what I have marked. So this should have been the last slide you saw. And I think we talked about, what is significant about this table. So I'm going to pop back a little bit and just as a review. So let's go back to standard hydrogen electrode. So recall that on standard hydrogen electrode, this can be used as a half cell in a voltaic cell. And so it's for a reaction between hydrogen ion, so H plus, and a reduction of that to produce hydrogen gas, H2. And we're making that to be like an equilibrium, so we're putting in hydrogen gas here. And the idea is to keep a constant pressure around the electrode. So we want it to be at 1 atmosphere so as to make it a standard potential. The idea is that the atmosphere is pressing in at 1 atmosphere. So if we just have hydrogen barely bubbling, then it's roughly 1 atmosphere. And that's some of the challenge of doing this experiment, is getting the flow of the hydrogen gas adjusted so that it just is starting to bubble. So that would indicate that the pressure is at 1 atmosphere. And anyway, with a standard hydrogen electrode, electrons could go in either direction. So this could be an oxidation, could be a reduction but we usually set it up to where it's going to be a reduction in the other half cell, so this is going to be an oxidation. So in typical situation, the electrons are going to flow like that. They're going to flow away from the hydrogen electrode and to the other electrode where we have a reduction happening. So now looking at our setup for this, here's an example. We are reducing copper 2+ cation, and we're making it into copper metal by taking electrons from the hydrogen electrode, so they're flowing over there. And then we read this number, and the hydrogen electrode, its potential is 0. Therefore, what we're reading on the meter is the potential just because of the copper. So we can do that with different substances, and we can then measure their standard potential. So here we're doing the same thing, except this time we have silver. So we're reducing silver cation to make it into silver solid. Same situation as the previous that we saw. But remember that for this to be valid, for it to be a standard potential, then the concentration of the cations have to be 1 molar. So, for the copper or for the silver, those would have to be a 1 molar concentration. And then we maintain the temperature at 25 degrees C. Then whatever number is measured is valid. Those are the numbers that we have in this table. So if I make this bigger, which I probably did this before, we can look for the two that we were interested in. Here is the silver. So we got a silver cation being reduced to silver solid at 0.8 volts. And then we also are interested in copper as an example. And so it's going to be reduced from copper 2+ to copper at 0.34 volts. So that's where those two numbers come from. And then we talked about in general for this table that whatever is the most positive is the best oxidizer, whichever one that's potential is the most negative is the best reducer. Hydrogen peroxide can go either way. It's in the middle of the table. So it could be either an oxidizing or a reducing agent. So then that was how far we got. At least that's what I have on my note. So now we're going to go to something new, and that would be the next slide. So we're going to take those standard potentials, and we can predict what would be the cell potential for a reaction. So this would be, what we're going to be doing this for is the voltaic cell that we started at. So it's for this one. So we are going to predict that this number should be a positive 0.46. for it to be a voltaic or a galvanic cell, it has to be a positive number. Now, that doesn't happen when we're doing measurements, because if we attach the voltmeter in reverse, what should have been positive will appear negative on the voltmeter, but it doesn't mean that it's actually negative. So that's how that happens experimentally. The number is still a positive 0.46, even if we're seeing a negative 0.46. Okay, so let's go back to this, and we're going to see how we calculate the cell potential. We're going to use reduction potentials in both cases. So these numbers would have to be given. You certainly are not going to waste brain space trying to memorize these numbers. That would be pointless. There's tables will be available that you can consider, and if it's just a problem, it'll be given in the problem. So we're going to take reduction potentials, and the main thing here is we want to take the one that is at the cathode. That is a reduction. Remember, cathode reduction. And we're going to subtract from that the potential that's at the anode. Remember, that is where the oxidation occurs. And we were doing a subtraction here. This formula is not going to be given. You need to just remember this. Okay? So you want to remember that you're going to subtract the oxidation from the reduction. Now this, in a way, it should not be that hard to keep it straight, because our table that we just saw, the table is all reductions. So we're not wanting to change the signs of those. So for the cathodes, which are reductions, we're leaving those alone. But in the case of where it's the anode and those are oxidations, then we're changing the sign. So that's what this negative is actually doing. So in a way, we are adding these together. It's just that we're changing the anode value, its reduction potential, into an oxidation potential. So here's two reactions that would have come from that table. There's our copper, and here's our silver. In the table, it said that for the copper, it was 0.337, and for the silver, it's 0.8. So that's what we got to work with. This is taken from the table we had on the previous slide. And then we're going to combine them together. Now here's something that we just need to remember, that we're looking for a voltaic cell. Therefore, the potential, the cell potential that we're going to get from this calculation should be a positive number. It needs to be greater than 0 for this to be spontaneous, which also is another way of saying, or voltaic is another way of saying it's spontaneous. So we could just take those two numbers, the 0.337, the 0.80, and we can come them together and see if we get a positive value. So in this first case here, we're taking the copper and we're making it the cathode, and we're taking the silver and we're making it the anode. If we do that, we get a negative number. So that's why there's a red line drawn through this. That's not correct. On the other hand, now, if we take the silver and make it the cathode, so I can't draw here very well on this. Not enough space. and then we take the copper, so the Cu2 plus, and make it the anode, then we get a positive number. So the way you do these is you just try them one way and then try them the other. And eventually, when you get a combination that yields a positive value, then you have it correct. So this is the correct one, where we got a positive value. So now we can take that information. Here is 0.8 for the silver. And so what that's telling us then is that the silver must be the cathode. Let's see, make sure I'm saying this right. Yeah, that's right. It is the cathode. And therefore, it's going to remain an oxidation. It's going to remain a reduction. That's the only thing about this electrochemistry. It's very easy to flip it around as far as whether it's an oxidation or a reduction. So you may need to draw things out to make sure you're keeping it straight. Now the other thing we're getting from this calculation here is that then we got the 0.337. That's the value of the copper. So that must be then the anode based on how we put it into the formula there. And so then that's the oxidation. So you can see how you're figuring out what is the oxidation, what is reduction, what is the anode, what is the cathode, based on what yields a positive value. Now, once we know which one is the oxidation and which one is the reduction, we can then take those equations and rearrange them. So since the copper is the, oops, let me change colors. Since the copper is the anode, or that's what's getting oxidized, then we need to rearrange this equation here so that it is looking like an oxidation. So we need to be losing electrons for this to be correctly written. So we're losing electrons. So we've got copper on the reactant side, copper 2 plus on the product side, and it lost 2 electrons. Now we're not going to change the potentials. Okay, we're leaving those alone because in our equation here, it happens at that negative side. Now the silver is the cathode. So we can just take that reaction. I'll change this color here. And we can use the equation for the silver as it was to begin with, as a reduction. So you've got silver, it's gaining an electron, it's becoming silver solid. Now the whole point of why we're taking equations and rearranging one and leaving the other one alone is so that we can then get to what is the overall equation for this reaction. So that's this bottom line. So we're going to take everything and bring it down to a new reaction. So the copper solid is on the reactant side, and the product of that oxidation is copper 2 plus, so that should be on the product side. And then we take the, and then we get to the electrons. And when we get to the electrons, we see that, oh, there's 2 electrons there, but there's only 1 here. So that means we need to take everything in that second equation and multiply it by 2. So that I've got a 2 in front of the silver cation, 2 in front of the electron, and 2 in front of the silver solid. Now I have the same number of electrons in both of these equations. So now when I take the second equation and add it into the first equation, I've got 2 silver cations on the reactant side, and I have 2 silver cations in the reactant side in the combined reaction. And the product is 2 silver solids, and that's what I've got in my final equation, 2 silver solids. The electrons, they both canceled out. So the 2 electrons here are canceling the 2 electrons in the first equation. So there's no electrons when we write out this process, because you've got the same number of electrons on both sides of the arrow. So anybody got any question then on how you get the cell potential, how you decide what is the oxidation or the anode, what is the reduction of the cathode, and how you would get the overall equation once you're done? I'll give you a chance if you got a question.
I wasn't present in last week, I mean not last week, but like on Wednesday's
Yeah.
lecture, so I'm a little confused on how you do the equation part.
Okay. You mean, are you talking about this up here? Because I don't think I talked about that yet. I might have, but I don't remember doing that.
Oh, no, like the bottom part.
Oh, that. Okay. Well, okay. Okay, let's go back to a previous slide. Let's go back to here. So here we've got copper solid, that's the wire, and we've got silver nitrate, that's a solution. We put them together in one container. We come back later on, and now we have got silver on the outside of the wire. So that's why it looks kind of brown and crusty looking over here. And we've made a new solution, it's copper nitrate, and that's why this is green now instead of being colorless before. So this process that happened in this single test tube is what's in this equation down here. So we've got copper, and then we have the ionic compound, but really the only part that's important here is the silver. The nitrate that's on the left side is the same nitrate that's on the other side. So we'll just leave that out, and instead now we're going to go from silver cation to silver solid, and then I'm going to change colors. We're going to go from copper solid to the copper that's in the copper nitrate, which is copper 2 plus. Now all this is happening in a single container. But when we go to, and this is an oxidation reduction reaction, but when we go to doing this as an electrochemical process, like we got here, now we've separated it into 2 different containers. So we've got the copper on one side, we've got the silver on the other, and we got the copper cation on one side and we got the silver on the other. So the equation, the chemical equation that we derived here is the chemical equation for that process. Whether it's in one tube like we did to begin with the wire in the solution of the silver nitrate, or if we do it in two containers like we have here. It's the same overall reaction. Does that make sense, Martiza?
Yes, it does. Thank you.
Okay, yeah, no problem. So now this slide just followed after where we were doing the calculation. So the next slide is this. This is just a repeat of what we had early on, and that is, that we observed that it was the potential with these two half cells is positive 0.46. We've calculated that it should be 0.46, and we went through figuring out what overall reaction is. Now here at the bottom is that shorthand thing again. So that remember that you can either use the shorthand or you can have a picture of what's happening. These are equivalent to each other. But be prepared that if you have a picture that you can make it into the shorthand, or if you have the shorthand, you can make it into the picture. So let's talk about how these are related one more time. You start out with your anode electrode, which is a solid piece of copper. That is this copper right here. You then move, you're basically going from here through here through here and over to here. Okay, I'm going to erase that so that we have a little clearer picture. So again, we start out, oops, get my pencil. We start out with our copper and we put that down. Then we're going to our copper 2+ cation, aqueous, so we put that in. Now since this first one, and it should have said solid, since this first one is solid and the second one is aqueous, then those are two different states of matter. So we have a line here, this vertical line that shows that this is an interface between two different states of matter, between solid and aqueous solution. We then get to our salt bridge here, and that's what the double lines are representing. It's as if one line is representing this end of the salt bridge and the other line is representing the other end of the salt bridge. Then the first thing the salt bridge is touching is the silver cations. So that's what we have here. They're in solution, so it's AQ. And then what you have left then is the silver electrode, which is this part. And again, that should have said solid. Now, since we have aqueous on one side and solid on the other, we indicate there is an interface between the two states of matter, and that's our vertical line. So again, if you see this shorthand, oops, if you see this shorthand, it means that picture. Or if you have this picture, you could write it in that shorthand version. Anybody got a question on doing that? Okay, we're going to do a worksheet on pretty much everything that we just went through on the calculation, where we're starting out with just a couple cell potentials. We're going to calculate a voltaic potential. We're going to use that calculation to figure out what's the anode, what's the cathode, what's the oxidation, what's the reduction. Then we're going to take that stuff and write an overall equation out for the process. And then we're going to end up with a picture of the voltaic cell, and we're going to label it. So let me show you where that's at in case you don't know. So I'm going to share my screen. I'm not there. Okay. And I'm going to Blackboard, and I'm going to click on Course Materials. So you're going to want to do that at home. And then you scroll down till you get to Worksheets. Click on Worksheets, and scroll down till you get to Electrochemistry. And then click on the one that's called Standard Cell. Standard Cell is what you want. And so it's going to look like this. So you want to keep that available as a tab on your browser. Okay, now I want to go back into Collaborate. So I'm going to stop sharing my screen, and I'm going to pull up the same file and share it with you guys. And so you've got here two different reactions, and you've got, they're both reductions is the way they're written. And so you've got the potentials. Now it's asking you to decide which one is the reduction, which one is the oxidation, but you really don't know yet. In fact, the best place to start here is at number 3. So I'll be asking you guys for an answer on that one. You're going to calculate the standard potential. So you're going to need to use that equation that we had earlier, where E cell is equal to the standard reduction potential for the cathode minus the standard potential for the anode. So you'll want to go back and refer to that. So anyway, you're going to use that to calculate the potential. Now, since you're going to have to pick one of these to be the anode, one of these to be the cathode to get a positive number, remember this is supposed to have a positive result, you then, by doing that, you're going to know which is the anode and which is the cathode. So you'll be able to answer these two questions. Number 4, number 5, what is the anode? What is the cathode? Then once you know which one of them is the anode, which one's the cathode, you're also going to know which one's the oxidation, which one's the reduction. So you can answer this question up here. And then you can take these two reactions and combine them together. But you cannot do it with them both being reductions. One has to be rewritten as an oxidation so that you can then combine everything together. And here's one more thing I want to say, that in order to combine those reactions together, in addition to taking one and flipping it around to make it an oxidation, you need to also make sure that you have these such that they have the same number of electrons, so they'll cancel out. Now, right now, they've got one has 2 electrons and one has 3. So those are not the same. You're going to have to multiply one or both reactions so that you get the same number of electrons. So you're looking for the least common value. And then after you've done that, you're going to fill out this picture. So you're going to write in each of these spaces a label using what you have in this list above. And I'll just say that everything you're seeing on this worksheet, you need to be able to do that in the case of an exam. Okay? So I'm going to make sure you guys are all in your groups, and I'll turn that on. You can talk about what you think the answers are, and then I'll come back and ask some folks. So let's check out, see if, yep, I've not gotten anybody new, so I think we're good to go. So I'm going to push the start button here and get you guys into groups, and then if you see you're in the wrong group, or if you have a question about doing this, send me a chat and I can respond to that. I'll give you, like 10 minutes to do this thing, and then I'll ask you for what you got as answers. So here we go. Start. Yeah, hey, that's okay. I think that's interesting what he was saying about fall, because some of the universities are already announcing that fall is going to be online also. And if you watch the news and everybody's got an opinion. I mean, it's all over the page. Uh, the mayor of Las Vegas is inviting everybody to come out there and drink and gamble and rub up against each other and just be right next to each other, and then take it all back to their home communities. So it's nuts. But anyway, right now we are here. So okay. So what I'm gonna do here, I've got it up the bottom part of the worksheet, and everybody has the ability to draw on here, or you can type. If you look at the top of your page, you see where the pencil is, and you can click on it, and then it'll let you, draw. It doesn't work real well, as you've noticed when I'm drawing. But anyway, then you can also click on the big T that's to the right of the pencil, and you can type, with that. Now, the one thing that's bad about Collaborate is the type is too small. So if you click on the arrow that's over to the left, you can then click on what you just typed and grab a corner of it and drag it and make it bigger, like that. So anyway, let's just do that, and we'll go around this diagram. So we're going to start right here, and then we're just going to fill in everything going around the picture. Okay, and I'll just call on some people. So I've got you guys in my attendance app, so I can just randomly pick you. So let's see. Here we go. Molly, would you type in, or you can use the pencil if you want, to fill in an answer for this first bubble? Okay. You want to see if you can make it big? Hey, nice job. Okay. So now let's do the next one. Oh, wait a minute. Oh. No, actually, I was getting ahead of the game here. I started clapping, but actually, that's supposed to be up here. So Molly, would you drag that over to the other bubble, please? I can't do it, but you can. Thank you. So we still don't have a name for this side. So what it's looking for here is you're wanting to label it as being one of the half cells. So uh, you want to go ahead and do that too, please. Which half cell is that? Going to be anodic or cathodic? Thank you. Okay, so now we'll get somebody else to do this bubble up here that's pointing over here. Okay, totally randomly selected. Edgar, would you please type into this bubble here what it's pointing to over here? Ah, okay. I will type it in for Edgar. Here we go. Let's see, aluminum solid. Okay, so we got that. Thanks, Edgar. And so now we're going to, oops, sorry. Okay, we're going to go to this bubble here. This is referring to the wire, okay? So that's referring to the wire. Uh, Brandon, would you type into that bubble what is going on with the wire, please? Electrons flowing to the right. Okay, I'll type it. There we are. I just really figured I'd give people a chance to draw on the board. You're probably going to get all excited, you know. Oops, I don't like that happening. Okay, so now we've got this one over here. So this is another electrode. And that person is not here. So let's see who else. Keon, could you please type into that bubble up here as to what is that electrode? Aha. And you want to take a shot at making that bigger for us? You do, use the arrow, you click on it, and you drag a corner. Ah, not working. Don't worry about it. I think everybody can see that. It's ZN. It's zinc solid. Okay, let's go down to what is in the solution. That next bubble down. And Brianna, please, would you type into that one? Thank you very much. And now we are down here to the label at the bottom of this side of the voltaic cell. Aurelie, would you please type in there what is the answer? Cathodic half cell. Okay, I'll do it. So we got one left here, and that is, oops, marker. And that is what's going on up here between the two cells. So we're on that last bubble. And Tran, would you type in there what you have, please? Ah, there we go. Okay, anion flow. Let's pop up and disappear way too fast. Let's see, anion flow to right. Okay, so we've got this all labeled up. Now, on an exam, of course, we don't do them this way. We have multiple choice questions. So you'd be, matching up in that case. So just be prepared that if you had a diagram, you could match it up correctly. And one more thing I want to say about that, and that is if it's a voltaic or also called a galvanic or also called a spontaneous cell, the electron, well, it's always going to be true actually, but the electrons are always going to go from oops, get my marker going. I think I'll change colors. Electrons are always going to be flowing from the oxidation or the anode over to the cathode or the reduction. So make sure you keep that arrow straight in your thinking. Now, I want us to fill in the shorthand part down here. So for this one, there's four parts. So remember, you start with the electrode and you go through everything through the salt bridge over to the other electrode. So I'll ask somebody to type in this first piece right here. So Noah, what would go there, please? Ah, he has aluminum solid. Hey, big aluminum. Okay, so now I'll get somebody to do this next part. I better make sure that, yeah, that's what I thought. Okay, I'll pick another person. Yulia, would you put in here, what is this next piece of the shorthand designation, please? Aluminum 3 plus aqueous. Okay. Okay. Now we are, oops, get my marker. How about over here? Next person is Janet. Janet, would you please type in there as to what is the next piece? Okay, it's possible she didn't hear me, so I'm just going to go ahead and finish it up real quick here. So this next one's going to be zinc. Oh, sorry. This next part's going to be zinc 2 plus, aqueous, and then this is going to be zinc solid out here. Yeah, that's right. Yeah, zinc. So anyway, we've got the shorthand completed. So like I was saying before, you need to be able to go back and forth between the shorthand to the diagram, back and forth. Okay, has anybody got a question on doing that? Doesn't look like it. All right, and our time is, well, I know technically we got 5 more minutes, but hey, I think this is a good spot to stop. So we'll stop here. We'll have our last lab on Monday and keep on pressing on. And I'll let you guys know if we're going to have an exam. But again, it could not happen until a week from, wouldn't happen on a lab. Yeah, it could. Well, yeah, it could happen because we won't be having more labs. It could be a week from this Monday. That'd be the soonest. Probably more like Wednesday. So anyhow, anybody got a question about anything before you all take off? Okay, it's crazy. Be safe. Take care of your people, and see you guys on Monday. Yeah, you guys take care. Be safe. Take care of everybody. Yes.